Atticus.
Hi, I'm Charles.
And I'm Kelsey, and our final project was the statistical analysis of bipolar junction transistor current gain. We begin with the project overview. Using MATLAB statistics toolkits and functions, the DC current gain, or beta, of bipolar junction transistors were analyzed. We then found various statistics, such as the mean, variance, and standard deviation, which were calculated for this parameter, and then we fit a normal distribution to the data. After that, we took smaller random samples from the total population to analyze. The width of the error intervals from these samples decreased as the number within the sample increased. The goal was to determine the n value required for a small sample to adequately represent the entire population. So part of our goal in this project was creating a MATLAB script which would be robust enough to handle a number of types of statistical analysis for various data sets. So we created a MATLAB file in which a user could directly input which Excel file they wish to open. This was designed to work both with XLS and XLSX file extensions. We also gave the user the ability to designate the alpha value for the error interval calculations. Our MATLAB script then processes the data and outputs a spreadsheet containing the desired statistics. Graphs for these statistics are also created. The user can input the name of the desired output file. Shown to the right is an example of the output spreadsheet. One can see here that this contains data on population mean, standard deviation, and variance, as well as the error intervals for mean and standard deviation for various sample sizes.
To be able to measure accurately all the beta values for the transistors, we created a 4-resistor circuit and then combined R1 and R2 together to make RB Thevenin, and then made an equivalent V Thevenin source. To be able to calculate B, all we had to do was to measure the voltage across RB Thevenin and across RC, and then divide the respective resistor values to find IB and IC, and then divide IC by IB to find beta, which is current gain. The 3 calculations we perform first in MATLAB are to calculate the mean, the standard deviation, and the variance. The values that we obtained from our data set were a mean of 157.29, a standard deviation of 6.411, and a variance of 41.109. This figure represents the probability distribution function of our data. The bar graph represents the probability distribution of our data, and we use dfit tool to fit a normal distribution function on top to show that our data fits normal distribution. This figure here represents our cumulative distribution function. The purple line is our actual data, while the red line was created using dfit tool to fit a normal cumulative distribution function on top.
So our population contains 100 beta values. Well, this brings up an interesting point. From these 100 beta values, what samples can we use to represent these 100 beta values? In other words, can we take a sample of 5 from these 100 beta values and then use statistics drawn on the sample of 5 to make accurate conclusions about the entire population? And this same principle could be used for sample of 5, sample of 10, sample of 15, all the way up to 50. For these calculations, we assumed a confidence level of 95%, and we calculated statistics for 2 parameters of interest, which were sample mean and sample standard deviation. Now, to take samples from the entire population, we used MATLAB's data sample function. So 100 random samples were taken from the population for each sample size. And the sample sizes we used were 5 beta values, 10 beta values, all the way up to 50 beta values with 5 beta value steps. So using that, each sample provides an error interval, and the error intervals for a set of 100 samples were averaged. So then the standard deviation of these averages were also calculated. So how did we calculate the error intervals for each sample that we used? Well, we essentially used, we started from the equation for confidence interval and then obtained an equation shown on the slide above me. And now these t-table values were obtained using MATLAB's t-inverse function, which basically just spits out a t-table value depending on your degrees of freedom and your alpha value. And then we did something similar with standard deviation, where we used the confidence interval equation and basically subtracted the lower bound of the equation from the upper bound of the equation. And again, the chi-squared table values were obtained with a similar MATLAB function called chi to inv, which basically spits out a chi-squared table value depending on the degrees of freedom and alpha value desired.
Seen here is a graph of our mean error intervals versus the sample sizes. For each sample size, we took 100 samples. We then found the average of the error interval sizes. These are seen in the blue dots. Plotted over the blue dots, we have red error bars. These error bars represent the standard deviation of the error interval sizes of the 100 samples. Here, we have the standard deviation error intervals plotted against the sample sizes. Once again, we see the same exponential decrease.
Our measured beta values fell well within the manufacturer's specifications. However, it should be noted that the manufacturer allows a very large range of possible beta values. One of the things we wanted to figure out was how large of a sample size is needed to accurately represent the entire population. Example, a company wants to know the mean beta value for a population of 100 BJTs with a maximum error of 3. What would the sample size be? Note, it is assumed for this first example that we're using a 95% confidence interval.
So going back to our plot of mean error interval versus sample size, we can find the number of samples required to get the error desired by the manufacturer. It can be noted that the max error is about half of the error interval when we're talking about these statistics. So we're looking for something, or a data point with an error interval of about 6. So we can see that samples containing 25 data points have an error interval of 6 when we also include the effects of the standard deviation. Therefore, if we have a sample containing 25 data points for this example, there will be a max error of roughly 3. From the plot of the mean error interval size versus sample size, we could conclude that the company should use a sample of 25 transistors to get the accuracy desired. So it would take a sample of 25 transistors. The average of those transistors' beta values would be within 3 of the entire population's average beta value.
The same sort of analysis can be applied to various confidence levels. Say we were to increase the confidence level to 99%. We can repeat the process. Again, we find a point with an error interval at around 6. Again, this will give you a max error of roughly 3. As seen in the graph here, this point occurs when we have roughly 40 data points within a sample. So in this case, the company would need a sample of 40 transistors in order to achieve the accuracy desired. This is to be expected when increasing the confidence level. So this is where things get really nifty. Remember that output file we were talking about earlier? So now, not only could a user view the specific data points in MATLAB, but it's also available in the output file created by the MATLAB script. A sample of this can be seen here.
Error intervals can be used to determine the number of samples needed to achieve a desired accuracy. The analysis performed in the previous example could be modified to any confidence level and maximum error. Statistics of samples are important to be able to make conclusions about product specifications. Example for writing specification sheets. Companies must balance the cost of testing and accuracy because ultimately they are responsible for the claims that they make on their specification sheets.
So what were some difficulties that we had during this project? Well, the first thing that was a bit challenging was keeping conditions consistent while measuring our current gains. In other words, making sure that each transistor was biased at the same Q point. Another thing that we had some trouble with was deciding which MATLAB functions to use. This took a bit of time to get the right ones dialed in. For instance, the chi2inv function and the tinv function, we decided to go with those over the param.ci function, which is now getting out to date and will be put out of use soon. And then finally, we had some difficulties writing code to fit the PDF and CDF functions without dfit tool. Dfit tool is nice because it can automatically generate code to generate the desired plots whenever you run the script.